So from now, we'll be recording whatever is going on in the desktop, and a video of that will be posted on the web. Not only you have the freedom to go look at the lecture notes, you can view or you can view those lecture again as long as you want. But I'm waiting for a better mic to show up. The inbuilt mic of the computer might not capture everything we're talking about. Anyway, so back to the optimization. So far what have we learned? In this chapter, we're talking about the dual optimized problem that corresponding to given optimized problem. And how do we get the dual problem? We look at the objective function. We look at the straightforward constraint function. Then based on those constraint functions, what do? We form a Lagrange function. Right? That's given objective function f0 plus a linear combination of fi and a linear combination of hi. Right? Once we have that, the L, then we minimize that L over x's. Right? And once we have minimized over all x's, then we get a function in terms of lambda and u. Right? And that's what we call the dual function. G is my dual function, and the constraint and we will want on that is we want that the lambda, the coordinates of the lambda must be positive. Right? And the reason we want that because if these lambdas, if we restrict the lambdas to be positive, then we have a lower bound on the optimal value of the primary problem. That the optimal value T star is at least always bigger than any value taken by G with that constraint of the lambda is positive and you can get it. Okay. So we were constructing some dual problem in our last time. What we're going to learn a little bit new today is what I promised last time was it's called conjugate of a function. So we're talking about so the Lagrange dual function is related to conjugate of a function. I'm pretty sure you have never heard about what do we mean by conjugate of a function. So all you know is from complex analysis that is conjugate of a function. Maybe in the function analysis you might have heard about the conjugate of an operator, that is the adjoint of an operator. Maybe not. You're in too big in place. So before talking about how the conjugate of a function is related to the dual problem, let's develop a little bit of understanding of the concept of conjugates of a function. So let's bring up the definition. The definition is straightforward. Suppose f is a sum function, real-valued function from Rn to R, any function. Then we define corresponding to that, we define the conjugate of f, denoted as f star, is again a function from Rn to R. Okay? And we define the function new function f star as for any value of y in R. So f star takes the value as you take the inner product corresponding to that, you take the inner corresponding to that y, you take the inner product y transpose x. Alright, so for a fixed y transpose x is now this is now a function of x. That is now a function of x, fx. Alright, you take the difference y transpose x minus fx. Right? But this part inside this it looks like a function of x while we're looking at y. But what you do eventually, you take the supremum over of this expression over all x. No, we do this for each y. Right? For each y transpose x, so y is fixed, so y transpose x is a function of x. That's exactly it. That's exactly what it is.
So it will be a function of x and y.
This is a function of x and y both. But for now, when you're taking supremum, y is fixed, x is variable. Right? So this is, once, forget this thing. Right? In this expression, y is fixed, so y transpose x is just a function of x, tan is just a function of x. You take the difference and you take the supremum over all x. Right? So this we are doing for each y. So for each y, we get a different thing on the right hand side. Right? So this makes the right hand side totally a function of x. Totally a function of y. Right? So geometrically, what's going on is, what is for each fixed.
What do we mean by domain of all x in the domain belonging to the domain? That means we are taking the supremum for each x in the domain. If we are fixing y, are we not doing supremum for each x in the domain? And then we are taking the supremum.
No, supremum over x means what? Fix a y here. Okay. Now once y is fixed, so now you start varying your x. For x equal to 1, 2, 3, you get some value. You get x equal to 5, 6, 7, you get some value. You get x equal to 120,000, you get some value. Right? So different combination of x giving me different values of x. Right? So this expression means that of all those different sources of x, you take the maximum value. So this, once you take the maximum value, that is then this just dependent on y. Okay? And there is no expression of x. Right? Geometrically, what this means is like what? This is simply saying, if you fix your y, then y transpose x gives the hyperplane. Right? So geometrically, what is this saying? Now y transpose x just gives the hyperplane. So y transpose x hyperplane with y as the normal vector, right? Correct? And fx is just some surface of the curve. Right? Fx fx is something okay. Oh, I broke that one, right? That's okay. Alright, so what do we have here? Y transpose x gives us it's a surface, it's a plane, and under that plane, I'm looking at and subtracting that with some surface of fx, right? And what are you doing? You're taking the difference between them and you're saying, look at the maximum of that. So basically, you're saying that you look at if corresponding that for each y gives a hyperplane, and this f, the conjugate of f star is measuring that like what is the if from the top how the surface is how what is the maximum the surface is going below the plane is defined by y. Okay? Right. So then this thing is simply then what do we have? Then this supremum over x of the expression y transpose x minus fx just measures what? That how much below f can go, how much below f can go below the plane defined by y. How much below? How much below f can go below, is it the English right? With the plane, below the plane defined by, does it make sense? Right? So this is the plane, and that's the surface. I'm subtracting, then basically I'm saying what is the maximum distance you can make in the below direction.
Should be asking how much it can go below the plane. And how much is it?
So yeah, that's correct. Thank you. Yeah, and for a simple one-dimensional example can be example is here. So let's say if there is a function defined by the black curve with these ones. Okay. Now each y here, so everything is one-dimensional now. So y transpose x is just y, is yx. So fix your y. So fix y transpose x is just yx, right? And for one dimension, so for one dimension, if you fix y, then yx is just a function. What is that? That's a straight line with y as the slope, correct? So yx denotes this line, blue line with slope y. Right? And what are we measuring? We are measuring yx minus fx. So blue line minus the black curve. Right? So for the pretty much most of the region, that expression is negative because here this thing is below, so this minus that will be negative. This minus that will be negative here. It becomes positive in this region, and again it becomes negative. Right? So basically, you're saying how much the black curve, how much below the black curve is going below the blue. So this f star. So f star y will be denoting just for this particular y, it will be just denoting that difference, right? So and again, then you move your y, then you have a different line, and then you again measure the same thing, same concept, with a different slope. And what will happen if the slope, if the line doesn't intersect the curve? Then we are taking the supremum of f, right? Not really. Not really. You're basically taking supremum of negative number. That's totally reasonable. Right? So for example, if we are in this kind of situation,